Okay, welcome to the second of the 3 lectures on Tetryonics that I'm giving over the course of this week. This lecture is going to assume that you basically understood everything from the last lecture and that you were present for it. If not, you can still stay, you're welcome to stay, but you might not understand anything. So today we're going to see my skeleton, or my incomplete derivation of this theory. We're going to talk about material properties, and it sounds very strange, but we're going to relate this to gravity. And after we talk about gravity, we're going to talk a bunch about cosmology. So like I said last lecture, in Tetryonics, energy is fractal. All of our large systems behave the exact same way as the small systems, just on a different scale. So we'll start, like I said, with this derivation. And I always wanted Tetryonics to have a more mathematical description and for it to come from previous knowledge, as well as for it to be more clear how you're supposed to compute things. So we can describe a force as being an overlap between 2 geometries, but then like how do we use this to say actually control a system or something like that? So we started making abstract lists of different logical steps that I would have to go through in order to actually derive it. And this is what I eventually settled on. Now this might not be a perfect one, but it's the best I've come up with so far. Not all of these have actually been completed, but I have a pretty good idea how to do all of them. So the first is to show that energy can and should possess a geometry. Sort of the most important one to start us on the path to creating Tetryonics. Second is to prove that this geometry should be a regular tessellation of the plane. Third one is to prove that of the 3 possible regular tessellations of the plane, triangles should be used, as this tessellation creates the standard normal distribution. So we saw that at the end of last lecture. Now many people have proved over the last, I think almost 100 years, that there are in fact only 3 regular tessellations of the plane. Or we mean regular tessellation as we have essentially one geometry, and we use it as a tile, and we essentially tile a 2-dimensional surface completely with it. And then we need to show that this 2-dimensional geometry for energy can be used to create 3D models of matter. Finally, we would need to show that of the 5 possible 3D geometries for matter, tetrahedrons should be used for some reason. This is the step that I essentially have done the least work on, and I basically have no idea how to do it or what criteria we should use in order to say that tetrahedrons are the geometry for us. Other than that, we already tried it and it works. So we'll start with step 1. And this is one of the steps that I haven't completed, but I'm pretty sure you could do it using Noether's theorem. Get rid of this. So Noether's theorem is a very important mathematical theorem from the standard model. And basically, it is a mathematical statement about the Lagrangian of a system. So the Lagrangian is usually describing 2 different dual aspects of a system. Say, a simple example is the kinetic and potential energy of a falling object. So when an object is held up high, it has a lot of potential energy. When we let it go, it begins to fall. And all of this potential energy is transformed into kinetic energy as it gets accelerated and moves faster and faster and faster. So in the case of a falling object in the classical Newtonian description, we essentially have the Lagrangian of the system as being simply the difference between the kinetic energy and the potential energy. Now Noether's theorem basically says that if we do a substitution on this Lagrangian, where we have some new variable q, and we make the Lagrangian solely a function of q, and we take its partial derivative with respect to q, what we have is that if this right-hand side of this equation is equal to 0 or a constant, then the time evolution of the amount of q we have in this system is conserved. So essentially we don't gain or lose any q if this right-hand side is equal to 0. So we can kind of think of this as we have a closed, isolated system, and we apply the conservation of mass to it. There's no inflow or outflow, so our total mass remains unchanged. We can also have this equal to a constant where, say, if this is equal to some constant rate of change, then we could have a condition where we have some kind of inflow or outflow, like if we were just filling a swimming pool with water. So the basic idea that I have in order to solve this first step is to re-parametrize either all the Lagrangians that exist for different systems. Like there's one that describes electric and magnetic fields. There are classical Newtonian ones. There are quantum mechanical ones. So I would re-parametrize those in terms of some kind of geometric variable, and then show that that geometry itself is conserved. And hence we have this equivalence relationship between energy and geometry. Now, I haven't actually done that because I don't know enough about Noether's theorem and the mathematics involved, like Lie algebra and group theory, as well as things like quantum mechanics in order to do that. But I kind of predict that that should be possible. So the second step is to prove that this geometry that is associated with energy should be a regular tessellation of the plane. Now this step I actually have no idea how to do, and there's essentially no reason for it to be true other than that it would be extremely convenient, because then we get this condition where energy is fractal and all of our large systems behave the exact same way as all of our small ones. Hopefully a successful proof to the first step would give some kind of clue as to how this should be done. The third step, to show that we should specifically use a triangular tessellation of the 2D plane. Because it creates the standard normal distribution, we basically already did that yesterday. We saw the numerical approach to proving it. Like I said, there are only these three possibilities for creating a regular tessellation of the plane, and we're not going to prove that. It's been done many different ways. So this step, well, we've seen the result, and we're pretty sure it's true. It's not, hasn't been done very rigorously in terms of just the math, and that's because the way that I decided to do that was to condense that renormalization algorithm that we saw yesterday into a single term, where here we're calculating the standard normal, the standard deviation, hopefully the normal distribution. And we need to take the limit of this as n goes to infinity and show that this equals to 1. Now, most computer algebra software programs basically give errors when you try to compute this, or they say that it diverges to infinity, which is obviously incorrect because we already showed that this converges to 1 within n equals to 3 to like a quadrillionth of a percent. Now, with regards to the fourth step, to show that we can use a 2D triangular geometry of energy to be used to create three-dimensional models of matter, this is another step that I have a lot of pretty good ideas, what I think are pretty good ideas, but I haven't completely hammered out all the details. So in order to do this, we need to use a bunch of different ideas from the mathematical field of differential geometry, where differential geometry is essentially the study of calculus on surfaces, what they just commonly describe as smooth manifolds. So the first useful idea from differential geometry is the way that a surface is even defined in the first place. So a surface is created out of things called coordinate patches, and that's what these are down here. So a coordinate patch is an open two-dimensional domain that has associated with it some kind of map that takes points in this 2D domain and then sends it to a point in a three-dimensional open set on a surface. So this is commonly described as we take the union of all of these patches, which creates the atlas of this surface, and these patches are essentially folded onto this surface in order to define it. Now, we saw yesterday that we said that chem fields literally fold into tetrahedrons. Now, this is not a description as to the physics as to how and why that happens. This is solely a mathematical description. as to how we can map the energy and the information onto the surface of a tetrahedron. So our second useful idea from differential geometry is the Gauss-Bonnet theorem. So what this mathematical equation says is that a sphere has the same total curvature as a tetrahedron. But it's actually more general than that. It says that any two surfaces that have the same Euler characteristic, which is this x here, or they belong to the same family of surfaces, is going to have the same total curvature. In the case of the Platonic solids that we see up here, these all have the same total 4 pi curvature, and it also includes the sphere. The sphere also has 4 pi total curvature. So this is useful because we can define points on a sphere in terms of essentially coordinates of curvature. You may be familiar with the idea that we have a parametric equation for the sphere that is made out of trigonometric functions that range over essentially an entire period of a trigonometric function. And this defines usually some kind of rotation about two different axes. We can call it, say, pitch is up and down and yaw. So we can essentially make two different circles that go around this sphere, one which is vertical and then one which is horizontal. And we can describe every point on this sphere as being correlated to some different pairing of a point on this vertical circle and one on the horizontal circle. But because a sphere has 4 pi total curvature and so does a tetrahedron, we can map every point on the sphere uniquely to a point on a tetrahedron through a one-to-one function called the Gauss map. So an intuitive description as to how this works is that if we have a normal vector on any one of these surfaces of infinite length, as we have it wander about this surface, it's going to trace out the shape of a sphere at infinity. So the reason why this is useful is because it potentially allows us to not have to recreate all of the mathematics of physics like we did with all the conceptual ideas. Normally, small particles are described as being point-like and they have spherically distributed properties. So we can take math that has spherical symmetry and potentially use the Gauss map to transform it onto the surface of a tetrahedron. Now there are a bunch of different problems with trying to do this. The first is that while the Gauss-Bonnet theorem guarantees that the Gauss map exists, it doesn't specifically tell us how to find it, but it does give us a bunch of clues. So the thing about coordinate patches is that they are not unique. A very simple example of this is going back to the parametric equation of a sphere, which we see up here. So because sine and cos are periodic, and they have a period of 2 pi, we could define this sphere completely by saying that phi ranges between 0 and pi, and theta ranges from 0 to 2 pi. But we could change this two-dimensional patch here and say, no, let's let phi range from 7 pi to 8 pi, and cos from 254 pi to 256 pi. We have a completely different two-dimensional geometry that creates the same three-dimensional surface. So what this allows us to do is to construct this Gauss map as a composition of transformations in a two-dimensional domain. So we say we take some kind of information that has been parametrized with respect to coordinates of curvature on a sphere. We map that back down into a two-dimensional domain. And then we map this to some kind of intermediate domain. This step might not actually be necessary. It's kind of just a general step. Maybe this domain here has some kind of nice algebraic properties that allow us to simplify things and make our lives easier. Then we go to an intermediate set for the tetrahedron's domain. We transform down into the normal domain that is easiest to map to a tetrahedron, and then we map it back to the tetrahedron. And we say that the Gauss map is the composition of all of this. So a very simple example that I have done is just equating the total energy on one surface to the other. So we know that particles are normally described by wave functions, which are once again trigonometric functions. And in Tetryonics we saw before that we essentially have a triangular wave describing energy. So the normal way that we equate the energy of two different waves with different geometries is by simply equating their root mean squares, which is this. We square root the wave function squared, and it's integrated over a single period, and then we average it over that period. So basically if we have two waves with the same frequency, we can just equate their amplitudes, and what we get is some kind of weighting function that says, well, it's like a linear transformation that says, like, if we have so much sinusoidal energy, it equals so much triangular energy. It's just a simple linear conversion factor. So the reason why I haven't been able to do this for quantum mechanical systems and other aspects of them is that I just don't know enough about quantum mechanics. So I haven't been able to do that. There is an additional problem with using the Gauss-Bonnet theorem, and that it works equally between all surfaces of the same family. And this is what leads us to our last step. So technically, any closed orientable surface that doesn't have a hole through it has the same total curvature as a sphere or a tetrahedron. Now, we already restricted our two-dimensional geometry to being equilateral triangles, and it just so happens that the Platonic solids are all of the different ways that you can tile a sphere with equilateral triangles. So because we have an equilateral triangle as our 2D geometry, we are likely restricted to only having one of the Platonic solids as the three-dimensional geometry for matter. So once again, we're left with this idea that we need to come up with some criteria to say tetrahedrons are the best. Hopefully, other than that, we tried it and it worked. Although that technically still is a valid mathematical proof. Since there's finitely many of these, we could just go through a process of elimination on all of them. That is a lot of work. So that's it for my skeleton of a derivation. As you can see, I've basically only done one step in it, but I think if these steps could be done, it wouldn't necessarily be a perfect derivation, but it would be pretty good to justify why do we even bother, and how do we not throw away everything that we already know. So we're now going to see how we can re-parametrize more quantities in physics, but in more of a mathematical way, and how this is related to geometry as well as material properties. And eventually we're going to essentially go off on a tangent into cosmology as a result of the way that we re-parametrize one material property. So we're going to start with the magnetic field. So basically, all I've done here is I said let amperes be equal to coulombs per second, so that's nothing new or crazy. And I said let kilograms equal to this energy per c squared that we saw yesterday. So if we substitute those in, and then we interpret this inverse seconds as frequency, when we simplify this, we get this result. We get a planar energy density multiplied by a ratio of frequency per coulomb. So this is kind of strange, and it doesn't necessarily mean a whole lot to us, and it's not very interesting, other than the idea that this frequency per coulomb is actually going to be a constant ratio no matter how much energy we have, because we always have this condition where one F is equal to one positive component and one negative component. What is interesting, though, is that if we do the same thing for the electric field, we get the exact same result, except that it is multiplied by a velocity. Now, I don't entirely understand why this appears, but I'm guessing that it has something to do with the Lorentz transform. So the Lorentz transform I briefly explained yesterday. If we have a bunch of stationary charged particles, we're going to measure an electric field when we stand close to them. But we're not going to measure a magnetic field. However, if these charged particles move to the left, say, with ever-increasing velocity, or they could just move to constant velocity, and say we're standing here, we'll measure an increasing electric field as they get closer to us, say this one, and then a decreasing one as it moves away. So what's going to happen is that as this geometry moves past us, or all these particles, we're going to measure a changing electric field. And due to Maxwell's equations, we know that that is going to create a magnetic field. And that the faster these particles move to the left, the greater the magnetic field we are going to measure. So we know that our chem fields that describe the velocity and properties of motion, of matter in motion, they have an uncancelled magnetic moment across them. It was what we were describing yesterday. So we've already seen how the Lorentz transform is essentially built into our description of a chem field. And essentially, what we can interpret this as is that, once again, only the electric field is moving, and what's going on here? What we can interpret this as is that only the electric field has velocity components that contribute to net forward motion, and that the magnetic field is essentially attached to the electric field and just gets dragged with it as it moves. So we can now re-parametrize epsilon using the exact same relations. So if we start here, and then go down to there, and up to there, and then down to here, it's all just algebra, we get charge squared per energy meter. So it's kind of helpful if we describe what epsilon even is in the first place. So epsilon is a measure of how easily a material will allow an electric field to be established within it. So essentially, materials that have a high epsilon, they're usually polar. And what that means, if we look at, say, this kind of picture trying to represent a water molecule, we know that water is made out of 2 hydrogen atoms and an oxygen atom, and that the hydrogen shares its electron with the oxygen atom. So what ends up happening is that we essentially have basically a naked 2 protons on this side, because the electron spends most of its time in here, and then a bunch of negative charges around the oxygen atom. So what we end up with is a separation of charge across this water molecule. So we essentially have a positive electric field over here and a negative electric field over here. Or, yeah, that's what it should be. This picture is backwards. But we essentially have a geometry like what we saw for a magnetostatic field yesterday. So what ends up happening is that we saw before that electrostatic fields create forces due to overlap. So if we take a large source of electrostatic field and we move it close to this water molecule, it's going to cause it to essentially orient. It's going to spin because the positive charge will be, say, repelled if it's a positive field, and the negative will be attracted, and it will rotate. Now, if we have some kind of collection of water molecules, because they have positive and negative ends, they bond to each other in a specific fashion. And this is what gives water the ability to form droplets. So the water molecules have a preferred bond orientation, where it's almost like, even though it's a liquid, it has almost a crystal structure. So when we bring a large electric field through water, it's going to cause these water molecules to reorient, and we're going to break its preferred bond orientation, which arises due to these molecules minimizing their potential energy, and it's going to give them a new orientation. Now, in order to break those bonds, we have to do work in order to displace this molecule. And that means that what is happening is that this epsilon is essentially storing energy, almost like it's a spring. Now, understanding all of that, we can basically see that this kind of makes sense. That if we have a high epsilon, we have a large amount of charge squared, where we're saying that we're ignoring its polarity, it's both the positive and negative. And we have this energy meters, which we can interpret as a one-dimensional flux of one geometry into another, because we know that force is created by the overlap of different geometries. So we can once again do the same reparametrization to mu, where mu is sort of like an inverse of epsilon with regards to material properties. A material with a high mu will easily allow a magnetic field to be established within it and pass through it. So when we do this reparametrization, we get something that kind of does and does not make sense depending upon whether this acceleration that we see here is a radial or a linear one. So high mu materials in general are not as conductive as low ones. So this doesn't really make sense if this is a linear acceleration. Oh, sorry, it doesn't make sense for a radial acceleration. Wait, sorry, my notes are all messed up here. It doesn't make sense for a linear acceleration. And then we know that materials are generally thought to have a high mu if they easily allow charge to circulate around small loops, basically, within themselves. Because once again, we create this changing electric field. It creates a magnetic field. This magnetic field superpositions with the external field and makes it stronger throughout the material. So if this is a radial acceleration, it kind of doesn't really make sense because we require a lot of energy to create this radial acceleration in order to increase the magnetic field. But then once again, we could say that the opposite is true, that it's it would be a very small acceleration for a large energy, basically. So in a nutshell, it's not entirely clear what this means. But for now, we're going to move on to the epsilon mu product. So this is a well-known result in physics that their product should equal to the inverse of the speed of light squared. And that what we find is that we get an inverse velocity, which we can interpret as being the speed of light squared. Because once again, we're working in a radial, relativistically normalized unit system. So we can also make amperes into something else. Before, we described it as a coulomb per second moving past a point. Now we saw yesterday that having a net charge is actually a very special property, and it's not a very general description of energy because only certain things have a net charge. But we did redescribe mass as being an energy per planar area. Now, essentially, because we did that, everything has mass. So we can redescribe amperes as simply being a mass flow or an energy flow past a point. Now, this seems odd, but once again, we saw yesterday that things that have electric field components, they might not necessarily have a net charge, even though they still have an electric field. So this is sort of a more general description of a flow of charge, even though we're talking about an energy or a mass. We're going to very soon see that this is essentially talking about displacement current and free electromagnetic waves that, say, light is an example of, visible light. And then the coulombs per second is specifically talking about charge carriers, electrostatic charges like electrons moving past a point. So when we do this reparametrization, we get a planar energy density per an expanding volume. So it's volume with the second derivative with respect to time. So this is going to make a whole lot of sense at the start of our next lecture when we suddenly see the three-dimensional geometry for these quanta, which they do have. It sort of relates to the idea of Doppler-independent redshift, in that energy expands as it propagates. But for now, we're going to ignore that this is changing in time, and we're just going to say, or even that this is a planar energy density, and just say epsilon is a density of energy per volume, regardless of what that energy is. It includes things with electrostatic fields, so like a net charge. It includes things that don't have a net charge. We just lump all of it together all at once. So we can also do the same for electric and magnetic fields, and we get something very interesting. First is that electric field gives us an acceleration under this re-parametrization, which actually makes sense because we can interpret this as being normalized with respect to some kind of test charge, the way that the electric field normally is in the standard model. The second is that we get the magnetic field is equal to a frequency, which once again makes sense when we think about the idea of the Lorentz transform, and that if we have a constant magnetic field, we have a bunch of charges moving past us at a certain rate. And so we can say that this is once again normalized with respect to our unit charge carrier, some kind of flow of it going past us. So if we do that same displacement current re-parametrization of mu, it's just more algebra going from here to here, down there, back up to there, and then down. And if we essentially just flip this meters cubed per second squared over, we get, once again, basically the inverse of epsilon. So epsilon, we saw before, the force is created by overlap regardless of what is overlapping, and then epsilon was a planar energy density per volume. So we can think of epsilon as being like springiness, like how tough is this material or this region of space going to push back on us when we push on it. And we can see that mu is something of an inverse of it. It's kind of more difficult to wrap your head around what mu is, and even I don't entirely understand it, but what I interpret this as meaning is this is almost like momentum. Like once we push something with the high mu, it keeps going and going and going.
That would be roughly analogous to admittance to impedance.
Yeah, exactly. It's a good point. It's exactly like epsilon is impedance, and then mu is admittance. Now we can do once again see what their product gives us. And it will give us the inverse speed of light just like it's supposed to. So now before we move on, I want to reiterate something about c squared that we saw yesterday. And that is that it can mean multiple things, potentially all at once. So the first thing that it can mean is we can be using it as an arbitrary area that we have simply defined. And say we can relate it to mass, where we just count up the number of quanta within this arbitrary area. Now, this mass can change by us just adding more quanta into this geometry. But once again, it's important that this c squared was arbitrary. And we also know that quanta experience wavelength contraction. So this c squared, if we associate it with the literal area that these quanta take up, it can create a change due to quanta either shrinking or expanding due to the energy content of a geometry changing. So that is an additional way that we can interpret it. And then the final way is that we said that these quanta oscillate and that we have a constant change in area for every single one. So once again, we get c squared as a changing area, but it's bounded essentially. So we have this maximum that it stays within, and they start here, they shrink into a line, they basically flip over, and then they expand out again. And they just cycle like that. So we essentially have expansion, contraction, addition, subtraction, and what we're going to see later is that this is actually rotation in three-dimensional space, that this entire chem field is rotating. And what this changing area is basically the projection into our reference plane. So this is very odd, but we can use our definition of epsilon and the idea that force is created by overlap in general to actually create gravity. Now this is going to be very strange, and it's going to involve the last assumption that we're ever going to make in these lectures. And that is that the inside of a tetrahedron, one of these tetrons, has epsilon and mu equal to 0. So essentially the inside of a tetron is the only place in the universe that is completely empty of energy. Everywhere else in the universe, it has particles, it has photons, it has electrostatic or magnetostatic fields of some description. And we, as part of one of our core assumptions about energy, we assume that it wants to expand to its minimum energy density and reach equilibrium. So what this means is that a large collection of matter all sitting in one spot, it looks like a hole to energy that it's going to want to expand and fill. And this is the force of gravity in Tetryonics. It's a lot like hydrostatic pressure in fluids, but in this case, the medium is energy itself. We're going to see soon that there's actually an even better hydrostatic analogy as to what is going on with this. So the mass matter content of these tetrons doesn't influence the force of gravity. The amount of excluded volume to energy's expansion is what creates a large force. Now, dense materials that have a lot of mass matter, they usually have a high tetron density. This, coupled with the idea that if they have a lot of mass matter, they have a lot of inertia and they're difficult to accelerate, creates all the same interactions that we normally expect of gravity, except once again, for completely different reasons. This gives us the very interesting condition in Tetryonics where gravity is not actually a fundamental force. It is, in the most general sense, the result of a gradient in energy density. On the exterior of matter, we have a high energy density, and interior, we have low. So this creates essentially a gradient in the density, which basically creates a pressure. And that's what gravity is. Now, this is actually almost exactly like Einstein's description of gravity in general relativity, where once again, he used the stress energy tensor to describe gravity as, in general, a gradient in energy density, except that the relative densities have been flipped. So he said matter is high energy density, the vacuum is low. We are saying it's the opposite. So in the most general sense, the idea that a gradient in energy density creates a force is true. We can use this simple example of Newtonian kinematics and the acceleration due to gravity of a falling object. So if we have a constant acceleration over a certain distance d, we can calculate the final velocity based upon the initial velocity, which is in this case obviously 0. But if we multiply by m over 2, we can get the kinetic energy on this side. And then on here we have something else. If we take the partial derivative of this, something else, with respect to distance, which I called x here, even though this is d, we obviously end up with a non-zero gradient, which we know corresponds to a force. So this is essentially true of all forces, that in general, a gradient in voltage creates a current, which has an electric field which produces an acceleration on charges. We know that a gradient in pressure is going to create a mass flow of some kind of fluid or liquid or something like that. So we know that this is essentially true, and that gravity, in a sense, is the most general description of force. It's sort of the most general force that can occur because it lumps absolutely all of the energy together, regardless of what it is. So once again, we come back to this idea that there's a lot of photons and a lot of energy here. There's not as much here due to the inverse square law. And we're going to quickly see that it's not just photons that are creating gravity. It's the magnetic fields of the Earth and the Sun. And we're also going to see that Tetryonics predicts that they have electrostatic fields, which a lot of cosmologists are probably groaning about right now, because this is actually a very old idea that many people have put forward before, the idea that electrostatic and magnetostatic interactions are significant on planetary, interplanetary, interstellar, and even galactic scales. But we're going to see that there is actually some evidence for this. So I described before that gravity is sort of like a hydrostatic pressure. That's not as good a description as we can come up with in fluids. There's something called an immersion force. So we saw before that water is polar. It has a positive and negative end. So as a result, it likes to stick to things that are also polar. So say like glass. But if it is not polar, then the water prefers to stick to itself because that will minimize its potential energy, and so it does. So this is the way that we normally describe things that are hydrophilic, which are polar and they attract water, and hydrophobic, which are nonpolar and they repel water. So if we put a particle inside of water that say is hydrophobic, it's going to repel the water molecules. And what's going to happen is that this is going to perturb these water molecules from their preferred bond orientation in such a way that it creates a gradient in the density of water molecules about this particle. Now what ends up happening is that if we have two hydrophobic particles and they get close enough that these gradients in water molecule density overlap, it will create an attractive force, which is called an immersion force. So this is a very, very good, almost completely equivalent description of gravity, except that once again we're talking about just a gradient in energy in general about these particles. So this is opposite to the idea of electric poles, where opposite electric poles will attract. When we're talking about capillary poles is what these are called. Capillary poles of the same polarity will attract. Where once again we see this idea that if we have a lot of matter in one spot, it creates a hole to energy. So if we have two holes and they're close to each other, they will start to orbit each other basically. They'll be attracted to each other. So this description of gravity does a lot of weird and interesting things. And the first is that it allows us to create Doppler-independent redshift. So you're probably familiar with the idea of Doppler shift. And we're essentially saying that Doppler-independent redshift occurs in addition to Doppler shift. It doesn't replace it. So Doppler shift is the idea that if you have a moving source of a wave, if it's moving towards you, if we're standing up front here, we can see these wave fronts pile on top of each other because it emits at a finite frequency and moves with a finite velocity. So it's going to emit here, and then before it can emit again, it travels to here. And these essentially get closer together. So if we're standing here, we're going to measure a higher frequency than if we were standing here and it was moving away from us. So this is Doppler shift, the idea that a moving source of a wave changes its measured frequency from our perspective, whether it's moving toward or away from us. Now, Doppler-independent redshift is going to occur regardless of the source's motion relative to us. If it is stationary relative to us and far enough away, its emitted wave is going to shift to a longer wavelength and lower frequencies, even though it is stationary relative to us. And this is because of the idea that we used a finite geometry for photons and energy. And this is very closely related to gravity. So if we said that each one of these rays was the path of a photon, we can see obviously that it becomes less dense out here. So the intensity out here, where we say that's the number of photons or the energy per area, if this is say like the surface area of some kind of sphere about our source, out here on a very big sphere, the intensity is lower. But what ends up happening is that the flux is still the same, because while the intensity decreased, the amount of area increased. And then we get this in the inverse result of that if we go inward. So here the intensity is very high, but the total flux is low because we don't have as much surface area. So we can relate the intensity between here and here through what is called the inverse square law. We say that this intensity over this intensity is proportional to, I might be mixing up which one is on top, but I think it's this radius squared divided by this radius squared. And what's interesting is that works for absolutely all fluxes in physics regardless of what the physics involved is, because this is purely a geometric phenomenon. It actually has nothing to do with physics. So what we get through the inverse square law and our finite geometry for energy is that up here, these photons overlap a lot. So say like the fraction of their total area at that distance from the source that is overlapping is very large. But as we go further away, their fractional area of overlap decreases. Now we know that an overlap of energy creates force in Tetryonics. So essentially what we have here is that this central photon is being squished, but out here is not. So as these photons travel outward and their intensity decreases, there is less force pushing them together, and they essentially relax, they expand outward. And this is what creates Doppler-independent redshift, in addition to another source that we are going to discuss during the next lecture. So we saw before that like mu, like he said, is equal to the, is sort of like an admittance of a material. We're going to see that photons essentially have a high admittance because of the idea that they have reinforced magnetic fields. So as they propagate, their energy essentially gets thrown outward. So close to the source, they are actually constrained by this overlap from expanding as much as they would like, and then here they are free to do so. And this is essentially what we're seeing here. On the electrostatic field, there's this magnetic zipper that binds these together. And so even though they have opposite velocities, they cancel and create no net motion because they're held in place, these two chem fields. On the photon, we don't have that. We have repulsion along the center. And so their divergent velocities diverge. They're free to diverge, and so they do. Now this has a lot of important implications for astronomy. The first is that people have inferred that the universe is expanding due to redshift. The idea that we look at distant galaxies and over time the wavelength changes to longer wavelengths. So we say, well, they're moving away from us because there is redshift. Like I said before, we don't dispute the fact that redshift is an actual phenomenon in Tetryonics. We say that there is an additional phenomenon called Doppler-independent redshift. So this is important because people have used the increase in Doppler redshift over time to infer the existence of dark energy and that the universe is expanding at a faster and faster rate. Tetryonics predicts that it's actually not. It's expanding at a constant rate. And that dark energy does not actually exist. We're soon going to see that it also predicts that dark matter also does not exist. This also has a very weird potential result, and it's that a lot of the cosmic background radiation could simply be galaxies that are so far away that we will never be able to detect them because their wavelength has shifted so much. And that the universe could essentially be incomprehensibly, unimaginably gigantic. So this description of gravity also gives us an opportunity to travel faster than the speed of light, which is very intriguing. So we saw before that like capillary poles will attract. Well, we have this condition in fluidics that opposite capillary poles will actually repel each other. So if this creates a low gradient, or a gradient in water molecules that goes from low to high, and this one goes from high to low, they will actually repel each other inside of a fluid. So in theory, if we could somehow create a region of high energy density next to a region of low energy density, we would create a gravitational force going from high to low, just like we have a pressure gradient from high to low. And we could accelerate something using this gravitational field. Now, something that I kind of skipped over last lecture is the idea that, so we have a diminishing rate of returns on the amount of velocity we get out of an acceleration because these chem fields grow in odd numbered jumps. But there's technically nothing restricting us from having as big a chem field as we want. As long as we can get the energy from somewhere, we can continue to go faster. So this, once again, it produces the same results that people witness, where it gets harder and harder to accelerate an object once you get close to the speed of light, but once again, for a completely different reason. Now, the way that we can create a region of high energy density and low energy density is by influencing the path of photons nearby a star. So we've seen, once again, that force is in general created by overlap regardless of what is overlapping. And so in theory, we should be able to affect the path of a photon using some kind of electromagnetic field. We essentially already know that this is true due to material properties, that we can have reflections off of glass. We saw, I described before, the glass is typically a kind of a high polar material. So it has a lot of these, there's no net charge in it, but there's these separated electrostatic fields. And so if Tetryonics is true, we infer that that is what is actually creating this reflection of light out of the material. But we can already see that, say, the gradient in energy density that we'd have to create is extremely huge. We can see that by essentially multiplying any number by Avogadro's number, which is the number of atoms per mole of a material. So the resulting flux of all these different overlapping dipoles is huge. And we might not, in fact, be able to create it with some sort of classical electric field source like a wire loop or something. But there might be a way that we could reduce the required electromagnetic field magnitude through the clever use of geometry. Now, there's a phenomenon known as dielectrophoresis, where if we have a polar molecule and we put it into an electric field that is curved, say like this is the electric field going from positive to negative, the negative part of the water molecule will want to accelerate this way, tangent to the electric field, and the positive will want to go that way, tangent to the electric field. And as we can see, what we've created is an attractive force perpendicular to the curvature of this electric field. So the magnitude of this force is proportional to the magnitude of the electric field, but it is also proportional to the curvature of the electric field. If we had a higher curvature, we would have less horizontal components and more vertical, and we would accelerate this water molecule faster. Now, this is not a theoretical force. This is something that people work on in digital microfluidics all the time. And I've actually seen it myself. Now we can create more curvature by essentially using pointier field sources. So because the electric field exists perpendicular to the surface of a metal, if we use the head of a pin instead of the head of a nail, we're going to get a more curved electric field. So we could essentially, well, we might be able to use this exact same process for either the magnetic field in a photon or the electric field, where we create a very curved magnetic field. And because we know the photon is propagating either into or out of the page, we'd want to create the magnetic field curving in like this and coming out like that. And then I'm actually not sure where the resulting force would go to, but we should be able to push it somewhere or pull it. Now this is going to require creating periodicity close to the scale of the wavelength of the photons, as well as having a large electromagnetic field density. And as well as a lot of curvature. Now there are these things called metamaterials, which once again, they already exist, where what people do is they essentially load a material with a lot of inductive and and capacitive elements in order to create what they call a negative refractive index. And these have weird and wonderful optical properties. They're called metamaterials because they don't exist in nature. They're artificially manufactured. Now these metamaterials work because the photon that is coming in is a changing electromagnetic field, so it creates a current inside of these repetitive circuit elements. And these repetitive circuit elements are their own source of a changing electromagnetic field, and they essentially provide a feedback onto the photon. If we're thinking about this in terms of Tetryonics, that there's now some kind of overlap onto a photon of decreased energy, and that is what is causing it to turn. So keeping with this idea, we could essentially increase the amount of force by taking the idea of a metamaterial, incorporating this idea of curvature and a high density, as well as periodicity close to the wavelength of the photon, but not equal to it. And the reason why we would only need it to be close is that we could force some kind of electrical signal to go through the material, and instead of having a passive system that has a passive feedback on the photon, we would have an active system. Now the reason why this might work is because once again we saw that these chem fields wavelength contract upon a higher energy content, so that our actual structure that we're designing in this material doesn't actually need to be as close to the wavelength of the photon as we might think if we just increase the energy. Now this has a lot of problems to do with optimization, because if we increase the current so much that our metamaterial is going to vaporize, obviously it is no good to us. But if we could do all that, we could essentially get a gigantic amount of energy out of a star without actually having to work for it. What we do is we put a field effect lens, is what I've come to call these, very close to a star, as close as possible. And the idea is that if this field, and not the material itself, can essentially part light around it, we can create a divergent lens where this material that it's made out of isn't going to vaporize even if it gets very close to the star. So we can create a very large divergence, because it's the actual field that this lens is creating that is diverging the light, and not the actual material. So what we do is we've created a low energy density corridor, basically, that is the closest thing that we have to a wormhole in Tetryonics. During the next lecture, we're going to see that space-time, essentially it doesn't actually describe space and time the way that we normally think about it. It describes the space that energy occupies, because they go through wavelength contraction, and the rate at which they're cycling. So we saw before, a high energy content geometry cycles slower. That's something that we assumed and that we're going to prove the next lecture. And we also saw that a wavelength contracts. So over here we have dense space-time coordinates, or we have like dense space coordinates, distant time coordinates, because we have time dilation here. And out here we don't have that. So this is basically describing what people would normally describe as a wormhole in the standard model. So we've bent space and time, but we haven't actually connected points. We've created a gravitational force along here. Now, it's very important to emphasize that this is basically the most dangerous device that it is possible to create, if Tetryonics is true. There's a lot of things that can go wrong with this. First, if the gradient in the gravitational force is high enough, you will be spaghettified, which is a real cosmological term, where the force, because the gravity is inversely proportional to the distance between two objects, even say over a couple of millimeters, the force is so great that you can just shear steel into millions of pieces. So that will obviously be bad. Second thing is that you can't steer. Once you're accelerated, you're locked into a trajectory until you reach your destination, where you would decelerate by doing this, the opposite of this at your destination star. So you can't stop and you can't steer, so if anything gets in your way, it's just going to be obliterated. The second thing is that by creating gravitational force this way, you're going to stretch this star. So you can alter its orbit, which is obviously bad for anyone living on a planet orbiting it. Second thing is that once this force disappears, once you and your lens are gone, it's going to collapse. And if it collapses too fast, we're going to see it could explode in a supernova. So there is a very interesting phenomenon that is uniquely predicted by Tetryonics, as far as I'm aware. I don't think it's predicted anywhere in the standard model. And that is something known as a gravitational electromagnetic pinch. And that looks something like this. So we saw before, matter is a standing wave. Because it's a wave, it can be interfered with like it's a wave. If we overlap a wave function with the right wavelength and phase match, we can nullify the forces that are giving these tetrahedrons structure, and they will explode, releasing all of their energy as light. So this is essentially antimatterless annihilation of matter. So this is predicted to actually occur at the core of a star in Tetryonics in addition to fusion. Well, fusion occurs in a star, it doesn't actually occur at the core, it occurs elsewhere, and there's actually a gem pinch at the center of every star. Okay, yes. So we saw before that electrostatic fields have a net outward velocity, even though they are static because they cancel, but they have all of this inward facing velocity as well. So we create this condition where if these geometries get big enough, this inward facing velocity will essentially crush anything at the focus of it. So this can be created by an electrostatic field geometry, it can be created by a magnetostatic field geometry. If it gets big enough, it will begin to tear matter apart at the center. We're going to also see that this is very similar to the idea of a black hole in the Standard Model. So this pinch inside of a star is maintained by a circulation of charged plasma. We're going to see in the next couple of slides that it doesn't need the charged plasma circulation to be created, but this will make it self-sustaining. So what we have here is that this is the hemisphere of the star viewed from the top. So it's a slice taken out of its center horizontally and then viewed from above. We said before, and we're going to essentially provide some evidence and arguments for this later, that stars have a net charge on them. So we're just going to assume that this is all positive plasma, or mostly positive, and that it's all moving in a clockwise direction like this. So as a result, these kind of act like interlocked gears, and it causes the entire star to rotate, which we actually see that it does when we look at it. Now this is a vertical slice taken out of the center of the star, where once again we have these plasma circulations that are coming out at the edge and going in at the center. If we obey the right-hand rule and we curl our right hand, we can see where the resulting magnetic field is going to point using our thumb. And we can see that this creates a circulation of a magnetic field within the star. So what happens is that this plasma goes into the center, it gets pinched by the resulting electrostatic field geometry, which we're going to see soon. This heats the plasma up and it convects outward. It is then constrained by gravity to not just continue expanding and explode, and eventually it cools because it radiates and it comes back down. Now these circulations, they are obviously inductive, and because of the way that these all overlap, they are mutually inductive, and so they actually help to reinforce each other due to the idea that this is creating a magnetic field. So as we look at this, we get this right-hand curl, and this is very interesting that it creates the exact same right-hand curl of a positive charge quanta. So once again, we get this idea that the electrostatic field, because it's two-dimensional, it doesn't make sense. But once again, we're going to see how this is a simplification of a more complicated system during the next lecture. Now, once again, it's important to note that this circulation of plasma isn't necessary to create the pinch in the first place, only maintain it. Technically, if we have enough convergent velocity and momentum, we will pinch matter. So essentially, a pinch doesn't care where the energy comes from or in what form it arrives at the focus, as long as it gets there with a high enough wavelength and a phase match. So there's this process known as sonoluminescence. So sonoluminescence is the process where if you vibrate a fluid enough at a high enough frequency, it'll start to emit pulses of light. Now this is normally described as we are creating cavitation bubbles inside of this water, for example, and then they collapse and it heats the water and then it causes it to emit photons. Now Tetryonics predicts that that occurs in addition to the creation of tiny transient gem pinches. And that if we wanted to, we could create a gem pinch and sustain it out of sonic pressure waves. That's just not a very efficient way of doing it. So now we can see why vibrating a star and stretching it and then causing it to collapse and then start to shake in and out is an extremely bad idea. We can accidentally increase the efficiency of the star's core pinch, and potentially create additional pinch sites at the nodes of the resulting standing wave. And this will mean that the divergent forces that are involved in the creation of a star will overpower the convergent ones of gravity and mutual inductance, and it will create a supernova. So once again, we come back to this idea that energy is fractal. We saw before that matter is in a continual state of dynamic equilibrium, so are atoms, and now so are stars. So we're going to see so are solar systems, so are galaxies, so are galaxy clusters. So this also leads us to our first scary prediction, if Tetryonics is true. So there is an idea for creating fusion reactors called inertial confinement, where essentially people have a gigantic amount of lasers or ion beams all focused at a central point where they put a fuel pellet and they superheat it and it fuses and releases energy. Now, if this is all true, that we can create gem pinches and stuff, then what can happen is that these reactors can have a much higher yield than anyone believes is possible. 1 gram of matter, if it was to annihilate, would release as much energy as the bomb that destroyed Nagasaki at the end of World War II. But we shouldn't really be all that scared or running for cover, because typically these reactors are trying to fuse micrograms of fuel, so that's 1 million times smaller. But this could still potentially be dangerous for the people operating them. There is actually a worse type of reactor than this, called a magnetized target. So magnetized target is you put a magnetic field over the fuel pellet, because once it gets heated into plasma, this will cause the plasma to travel in an arc as it goes outward, and it will expand slower, and you'll have more time for fusion to occur and a higher yield. But we saw before through the Zeeman effect and our description of the weak force that in general a large magnetic field makes matter unstable. So technically, once again, the reactors could explode without them ever knowing that that is even a possibility. But now we're going to talk about gravity some more. So once again, the gem pinch is created out of a circulation of charged plasma. We have to answer the question, well, how does it get a charge? Where did all the negative charge go? Once again, we come back to that idea that in order to create a pinch, we don't actually need a circulation of plasma, we just need that to maintain it. So we predict in Tetryonics, at least this is my interpretation, I don't know how Kelvin actually explains how this comes about, but early on in the star's lifespan, when the pinch is initially ignited, its output is high enough that it will eject all of the lighter charged particles of electrons out into the solar system. These will embed themselves in all the dust and all the planets and things like that that are currently forming and give them a net negative charge. So this is not as crazy as it sounds, because Einstein originally created the stress energy tensor to compensate for deviations in Mercury's orbit from that predicted by Newtonian gravity. So once again, the stress energy tensor says that gravity is due to an energy density gradient, and it also doesn't discriminate with regards to what energy has a gradient. It just says it's there, that's what gravity is. So in Tetryonics, we see that gravity is actually the net result of a whole lot of different things. Planets are in motion, they have chem fields, so we have a chem field. They have electrostatic fields, so there's an electrostatic field, and stars generally emit a gigantic amount of light, so there are photons of every description everywhere. So in Tetryonics, we propose that Einstein actually corrected for electromagnetic interactions he never knew were there. Now, these fields, like we said, are significant on gigantic distance scales. So this isn't drawn to scale, but the charge field of the sun is so big that it actually interacts with the charge fields of other stars. That's how big it is. Now, what's very interesting is that this actually does explain a couple of different interesting things about our solar system. And one is that we know that the sun basically spins in a certain direction, that all the planets spin in the same, or they orbit around the same direction, and they also spin in the same direction. So if the sun is positively charged and say it's spinning to the right, into the page, we use the right-hand rule, it has a magnetic field pointing up. Earth is rotating around to the right as well. We use the left-hand rule because it's negatively charged, it has a magnetic field pointing down. So we have an up field and a down field. These act like we have bar magnets that are flipped opposite to each other, and there's a mutual attraction between them. So we see that the planets are in a mutually inductive relationship with the sun. And this is once again part of what gravity is. We also once again come back to the idea that energy is fractal and that everything is essentially tending towards dynamic equilibrium. So now you might be wondering, well, why can't we measure this gigantic charge field that we should be able to measure? There's sort of two answers. There's a simple answer that we are going to essentially talk about more, but the more complicated answer is that we actually do all of the time. If the Earth is charged and it's moving and it has a chem field, it's going to create a magnetic field. The Earth has a it has like a magma core, which is, people describe it as plasticky, but it circulates, and there's in general electric currents that go through the center of the Earth. And essentially these electric currents help to stabilize this mutually inductive relationship between the sun and the Earth and enhance the Earth's magnetic field that it would normally already have, even just due to its motion as well as its net charge. So we can do a very simple calculation to also show why we would never be able to measure this electric field by calculating the distance over which we would measure a change in 1 volt due to the sun's electric field. So we have Ohm's law, voltage is equal to current multiplied by resistance. We change this for a current density multiplied by area, and we can calculate the voltage between 2 points. We're going to use the inverse square law, which, like we said before, works for all fluxes, no matter what they are, and a value for the average amount of current taken from the essentially flux density of the solar wind. Now, people might be saying that there is a gigantic problem with this and that the solar wind is measured to be net neutral. I'm not disputing that. But as far as I've been able to tell by reading literature, no one has ever measured or checked to see if the positive and negative charges are moving in opposite directions, which is what we predict is going on in Tetryonics. The sun is mostly positive charge, it emits positive charge. The planets are mostly negative charge, they emit negative charge. A negative current going in one direction will define a current going in the opposite direction. A positive charge going in one direction will define a current going in that same direction. So we say that there is a net current going through the solar system, and that it is basically acting like a gigantic battery. So we use this for our first J value. We can calculate the second through this. We have our first R value as being 1 astronomical unit, which is the maximum distance between the Earth and the Sun along the Earth's orbit. We use the intrinsic impedance of vacuum, and we can do the substitutions and calculate that our second distance point is going to be 10 astronomical units for a single volt. So vacuum is basically acting like a perfect short circuit. And we know that in something that is conducting, we typically can't measure a magnetic field or an electric field inside of it. What's also kind of interesting is that because our solar system is charged and is moving charge, it should emit photons, but of ludicrous wavelength. So over a star's lifespan, like I said, there's going to be a reunion of charge at the sun and at the planets, and eventually the sun's charge is going to deplete. So like I said, we need this charge to maintain the star's gem pinch. So this means that the star can now die in multiple different ways. The first is charge death. The sun's gem pinch eventually becomes so inefficient and so weak due to reunion of charge that it stops, and what we're left is a neutron star. Neutron star is made mostly out of neutral matter, where Tetryonics predicts, but we're not going to actually talk about this in any lecture, that there are actually neutral elements made out of neutrons and neutrinos. like I said, we're not going to go very much into chemistry at all, because I don't even know about that even in the standard model, so I'm just going to ignore it. So this neutronium that Kelvin has named it, it is extremely massive because we saw before that neutral matter has variable mass matter, and it is extremely, excuse me, it's extremely magnetic because we also saw before that neutrons have an intrinsic magnetic moment. So all the magnetic moments of all this neutronium superposition to create the gigantic magnetic field that we normally associate with a neutron star. The other possible death of a star that we're going to talk about is a supernova. So there are multiple ways that this can result. The first is that stars usually come in pairs. We have a big star and we have a smaller dwarf star. And over many millions or billions of years, they can eventually spiral into each other and collide because they're actually in an unstable orbit. We saw before that if you shake a star or you collapse stuff into its center too fast, it's going to increase the pinch efficiency, so this can cause the star to explode. We also saw during the last lecture that the magnetic field is weaker than the electric field, and so when a star does explode, it typically explodes outward through its magnetic polarization zones, like we actually see when we look at supernova. So we can essentially infer that the magnetic field was here, or no, it was here, and the electric field was here. So basically what's happened is that the star has almost pinched itself in the end. Another additional way that this can result, which is also kind of scary, is that the way that we have defined epsilon is not a universal constant. Not only does it vary between materials, it varies all throughout space. What Tetryonics predicts is possible is that a star can simply drift into a region of space where the established vacuum energies there will not allow for a star's finely tuned equilibrium to continue, and it will just explode. And that there's nothing that we can do about that. So we can describe galaxies using Tetryonics as well, where it is known that galaxies have a black hole in their center, and this helps give them their structure generally in the standard model. This is true of a lot of galaxies. In Tetryonics, we come back to the idea that energy is fractal. All the big systems are exact same as the small systems. We predict that there is actually a pinch inside of every galaxy, and this is what actually holds the galaxy together. This pinch is once again created by the circulation of charge. As we can see here, we have a bunch of stars orbiting in these circular orbits, very similar to the way we had plasma circulations inside of a star, where these stars are basically all positively charged like all matter stars are. But the reason why these solar systems have mostly one charge is because the gravity is so strong here that most of their planets can't maintain their orbits. They just get pulled away. And so we essentially have like naked positive charges here in the form of stars that are circulating and creating this pinch. So this pinch actually holds the galaxy together and causes it to rotate. Now, typically people calculate that due to the observable mass in the universe, there shouldn't be enough gravity to hold it all together to infer the existence of dark matter. We propose that if you include all the other interactions that are present but basically unmeasurable, you will show that there is no such thing as dark matter, that the universe is dominated by essentially plasmonic interactions. Now we know that black holes don't allow light to escape because the gravity is so high. In Tetryonics, we predict that light actually does escape. It comes out at 90 degrees to the plane of the galaxy. Where once again, we saw the same idea with the supernova, that the magnetic field is weaker. We have all this convergent electric field, and the only place for the energy to go is out the top. Now we actually see this in normal astronomy when we see quasars, which are pulses of light from other galaxies. So this is very interesting. Once again, we have this idea that everything is at equilibrium, and that a galaxy is a pinch, but the pinch is also the galaxy. It's kind of very weird, interesting. The final topic we're going to talk about is antimatter. So as far as the standard model can tell, the universe is dominated by matter and that there is no antimatter where there should be. We've seen in Tetryonics that antimatter is matter that has been turned inside out. So they're perfectly symmetric with each other. They behave in the exact same ways, but they have opposite field polarities. So it's very important that they behave the exact same way with regards to emission and absorption. So when we look out at other galaxies, we are likely seeing antimatter all over the place. It just doesn't look any different from matter. And Tetryonics predicts that these differences in circulation, which correspond to different polarities of magnetic and electric field, are what help give the entire universe its structure. Once again, we don't have dark matter, we have electric and magnetic field interactions. The only way that we can tell a matter galaxy apart from an antimatter one is if they were sitting in the same plane, and we could actually see them rotating in opposite directions. But this isn't a foolproof method because one could just be a matter galaxy turned upside down. We have no way of knowing. So although Tetryonics predicts that not only interstellar flight is very possible, but even intergalactic flight is likely, it is extremely risky because you might just explode upon arrival. So that's it for this lecture. Thank you all for coming. On Friday, we're going to go through and get even more mathematical than we even were at the beginning of this one. And we're going to see the three-dimensional time domain model for these quanta. And then a lot of our initial assumptions during the first lecture are going to become essentially self-evident why this would be true. So does anyone have any questions?
Kind of more of a comment. When you're talking about with the lens part,
Yeah.
I always forget the name. There was a fellow who had a model for interstellar flight where they were...
Negative energy?
Yes.
Yeah.
And it seems very similar, almost.
Yeah, it's almost, it is very similar. The only difference is that his sort of like warping of space-time moves with the ship, whereas ours is like you get one gigantic push and then you're gone.
But couldn't you use the same sort of lens to break, given that you would still have particles to maybe misunderstand?
Well, like you could use it for particles as well as photons. The idea that you'd put it close to a star is that you could create such a gradient in flux that it would create a huge acceleration.
And the gradient would, of course, be much, much weaker in interstellar space. But
Yeah, it would still be there.
you would still have some ability to break, but it would be much, 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 much less.
Yeah, like we didn't talk about this lecture, but there's actually a much simpler, much safer way that you could travel between planets and between stars. That's simply just polarize the hull of your ship. If you're next to the star, it's positively charged. Give yourself a positive on the outside, negative on the inner side. Just make sure it's really uniform so you don't electrocute yourself, and then you'll get shot off.
And you just rely on electrostatic forces of the galaxy.
Yeah.
I was actually going to ask about the, I think I might have just missed it, but you're talking about the magnetic field of the Earth.
Yeah.
And so you talked about the iron core flux, which they usually associate with magnetic. What was the conclusion at the end of it? There was almost a net zero because of the induced one? I might have...
What do you mean by net zero?
I think I just missed like the...
Okay, so I said the reason why we don't measure a gigantic electrostatic or magnetostatic field around a star, we do measure a magnetostatic one, but the reason why we don't measure an electrostatic one was twofold. There was a simple answer in that if we do the simple calculation, we'd need a voltmeter 10 astronomical units long. But the more complicated answer is that we actually do, because we know that an electric field is always paired with the magnetic field. We can actually infer that part of the reason why the Earth's magnetic field is so strong is because it is in a mutually inductive relationship with the sun.
Oh, okay.
So it has a negative charge and it moves, so we have the Lorentz transform, it has a magnetic field. It has circulation of that iron core, so we get an increase in the flux, where once again, essentially the sun's magnetic field almost like permeates the Earth and it is stabilized by this circulation of magma and charge and stuff like that.
So this would also somewhat account for, I think it's Venus and Mars have induced magnetospheres that are slightly weak.
Yeah. They would almost be like a permanent magnet, where we are essentially an active like solenoid, because we have radioactive decay and that heat inside of there is consuming power essentially.